Yilmaz Yoru. I am MVP of Embarcadero.
There
We
we
are
go.
a C++ builder, and IDERA companies boosting C++ builder and Delphi and other tools. Tokyo version is really great, and also Jim is really awesome man. We love him. Thank you. In this presentation, I am going to present multi-thread computational fluid dynamics example in C++ builder. This is something like simulating life, something like simulating fluid in a real life. My name is Yilmaz Yoru. I'm a mechanical engineer, and I am owner of the Essential company. I have 30 years in programming since college years, 10 years in academic area. I know more than 25 programming languages. And I have some scientific publications, articles, and presentations. We are mostly developing engineering applications, business applications with databases, 3D applications, some little games and automation, and artificial neural network and AI are current areas that we research now. In this presentation, I'm going to tell about theory of CFD and Navier-Stokes equations. Then I'm going to talk about model and boundary conditions and simple method and matrix model. And then SOR, successive over relaxation methods, and application and results. Theory of CFD is started in 18th century by Daniel Bernoulli, then Leonhard Euler, and then Claude Louis Marie Henry Navier and George Gabriel Stokes introduced viscous transport into the Euler equations, which resulted in the Navier-Stokes equation. This forms the basis of modern-day CFD. In the theory of CFD, there are two modeling techniques. One is Lagrangian method, and the Eulerian method is the other one. In the Lagrangian method, the grid moves and follows the shape of interface. Interface is specifically delineated and precisely followed, suited for viscous and laminar flows, problems of mesh distortion, and resulting in instability and internal inaccuracy. In Euler method, fluid travels between cells of the fixed mesh, and there is no problem with mesh distortion. There can be used adaptive grid techniques, and fixed grid techniques also can be used, like volume fluid method. Briefly, Lagrangian method means moving grid, Eulerian method means fixed grid. Moving grid is something like fluid drop, waves, mixing fluid. And fixed grid is flow in a fixed space, in a duct, in a channel, flow in over the car, over any object, something like that. In the theory of CFD, there are many numerical solution methods, and there are two popular methods, finite difference and finite volume. Finite difference uses nodes, and finite volume uses volume meshes. It is very good at 3D mesh models. Modern analysis software uses mostly finite volume, but also finite difference useful in standard models like rectangular channel flow, pi flow, and other flows. In numerical analysis, there are many methods and approaches about CFD: Mach formulation, upbit method, central difference method, hybrid approach method, linear upwind method, power difference method, local exact difference method, quickest methods, simpler, and simplex methods. In this study, we used simple methods. In the theory of CFD, there are steps of CFD analysis. First, define the problem and model. Formulate equations. Model the geometry and flow domain. Establish the numerical methods. Generate the grids or mesh. Establish the initial conditions on nodes or volumes. And also establish the boundary conditions. solve equations with matrix form with an iterative method, perform the simulation, graph results, and analyze. In the theory of CFD, in our study, we have assumptions here. We have rectangular channel flow, we have two-dimensional flow, X and Y only. There is no gravity, so we are looking from the top view. It is incompressible fluid or water. We have unsteady flow, that means it depends on time, so we have time change and time dependent graphics. We have laminar flow, and we have uniform flow inlet at the start. All nodes are same in X direction. Uniform mesh model we have, and a small block placed in front of the flow, as you can see in this image in yellow color. Now I'm going to tell about Navier-Stokes equations and how we use them in calculations. In the theory of CFD, the first equation is conservation of mass. These are those equations in X, Y, and Z directions. U, V, and W are velocities in U directions, V directions, and W directions. We have two dimensions, so we're going to use only those two equations here. And also, there's continuity equation derived from these equations. And we also use momentum equations here. And this is a 3D form, but we are using two-dimensional form, you know. And those are 3D equations here that you can use in X and Y and Z directions. Again, U is velocity in X direction, V is velocity in Y direction, and W is velocity in Z direction, and P is the pressure here. Mu is the dynamic viscosity. And so, as a result, those are Navier-Stokes equations derived from those two equations. And in calculations, we are using dimensionless equations, so you should make it dimensionless. Here is the dimensionless Navier-Stokes equation shown here in two-dimensional form. Okay, this is a simplified model for the rectangular channel flow. And it is two-dimensional. Flow area is gray, and pressure nodes are shown in big nodes. They are green, and velocity nodes, which are calculated there, are blue nodes. And if you look at the pressure nodes, there are simplified model here. And then if you look at the velocity nodes, in each node we are calculating U and V velocities in both X and Y direction. And at the wall, those yellow nodes are zero, because at the wall there is no velocity. That means both sides, U and V, is zero there. At the front, there are initial velocities, so U is zero in all front velocities, and V has a value. We used uniform flow section. And as a result, with hidden velocity nodes, you can use this node design model to calculate velocities and pressure in the fluids. model. We use simple semi-implicit method model for pressure linked equations for the velocity model and pressure model. This is how velocity model is calculated. The center of the center nodes is unknown. So we are calculating with those nodes here. And so we find the velocity at the next step. Again, with the same, there are pressure nodes, and we calculate the central pressure with east, west, north, and south nodes. And we also use some velocities in the equation. This is the pressure model. As a result, in general form, this is the very big formulation maybe for one node. So it looks like very complicated, but front of the P parameters, this is only pressure equation. Front of the P parameters, there are constant values. So as a result, we can summarize this equation like shown in the bottom equation. So we have only east, west, north and south and central pressures, and so those are unknowns. That means we have 5 unknowns in matrix. Also, this means you will have 5 diagonal matrices to solve this. As a result of equations, we have 5 diagonal matrices. This is an example for the u velocities, how to calculate new u parameters with this matrix. So we are using successive over relaxation method to calculate those kind of 5 diagonal matrices. If you are using 3D model, this matrix will be 7 diagonal because there will be up and down parameters also. And so if you want to do this in multi-thread, you should divide each lines or sum of lines to threads. So you can calculate whole matrix. You cannot divide to the different matrices because the next new matrix depends on the previous one. So first you should calculate the previous current matrix, and then you can calculate the next one. For example, in animation, they are using frames calculating in each trees. You can calculate them in different trees, in different CPU cores, because all is unknown. All the animation is known and modeled well. Each frame is known well. But in this situation, next matrix is unknown. So we cannot divide matrices. We can divide lines of the matrix here. In our study, this is our matrix form structure. We have D, D, E, F, H. That means top, bottom, left, right, and central parameters of the nodes. And we also have which number of the node is this. So east, west, north, and south nodes have numbers here. And this is the successive over relaxation method, how we calculate all nodes here. This is single core model. And if you want to do this multi-thread, first you should define class of the calculation threads. And this is our class. We have public worker number, workers work start and work end parameters, which line of the matrix you will start to calculate here, and which line of the matrix you will end to stop. You will stop the calculation. And those are the traits that we used here. Here is the application that we generate. There are a lot of unknown nodes, as you see. Those are shown in vector form, and we have a block which is shown in yellow color in the middle of the flow. So we want to see what happens in front of the flow, in front of this block and behind the block. So we want to simulate this. As a result, after calculations, we obtain different views of the fluid's behavior in different time periods. At the end, you can see vortexes and vector changes on the form, and we also obtain graphical results in color modes for the U, R, and P parameters. And now let's see how this theory and method is working with C++ Builder. This is built with VCL form, and actually in 1999 that was the first build, and it wasn't accepted, but I spent a lot of time, so I want to show this old version here. In this old version, it's also built with C++ Builder, and you can see each nodes here. For example, those are pressure nodes here, and each node has value at the start. This is fluid flow. And also we have vectorial form here. So you can see each vectors on the fluid form. And when you calculate, you can see uniform fluid flow here. And you can also add some blocks here, like this, to see what happens when there's a block inside the fluid flow. As you see, it is working very fast, but there are no vortexes behind this block here. But it is very nice to show how fast C++ Builder is calculating, because there are a lot of unknowns and there are very big matrices to solve, and it's solving each nodes very fast with many iterations. You can also see iterations, how many iterations done to achieve the enough approach. So it is very nice to see what happens when there's a block here. Now let's see our current version.
Hi everyone, seemed to have a sort of unexpected end to the video there. Just looking into what happened, perhaps it wasn't fully downloaded. So our tech experts are looking at it right now. I believe Yilmaz, you're online. Is that right?
Yes, I am here.
Fantastic. So I assume I'm right that that wasn't the end of the video, was it?
Yeah, there's the end of the video here.
Oh right. Okay. Well, look, let's move on. Sorry, I had some issues there, being muted myself. So looking at the Q&A, we have some people saying thank you for the presentation. Yeah, I agree there. This is very interesting. I'm particularly looking forward to this one as something to watch. A bit of a question about the speed of the calculations. Is it possible to have something that draws real time on, well, not real time on screen, but sort of animated on screen for very small or large sizes?
Yeah. We are using a lot of nodes here, so it takes time because it is doing iterative approach with the successive over relaxation methods. So it is calculating again and again till it has little error. Then it says, oh, it's okay. So it calculates the time and then passes to the next matrix model and calculates the new one. So in this method, that takes much more time, but it calculates very precisely.
Well, I guess preciseness is important depending on what you use this for. I mean, I've seen these kind of things used for screensavers and that kind of thing, where I assume that being precise doesn't matter, but when you get down to actual simulation for scientific and engineering work, it would need to be accurate. But what kind of performance do you see though? I mean, is it possible to have something that is smooth and visual on screen? When you mentioned the sort of over and over getting down to higher and higher levels of accuracy, what kind of what kind of code behavior do you see? What's involved there?
In this project, can you repeat the question?
I was just wondering about the complexity that you see when you say that it repeats calculations over and over to get down to a certain amount of error.
Oh, okay. It is calculating pressure and U values, but there is difference between the exact value of that time. So it is trying to approach as possible as it is corrected. It is well explained in Patenkar's Computational Fluid Dynamics book and other computational fluid books. At the end, there were some book links, but I think we are not able to show the end of the presentation. And so you should have to calculate this, and you can speed up by decreasing the error function. In this model, I think error function is 0.0001 or something bigger and something smaller. And so if you use bigger error functions. Hello developers and Embarcadero. This is Yilmaz Yoru. I am MVP of Embarcadero. We are very happy with C++.
Okay, so I think your video accidentally just interrupted you there. Please continue. Jim is working in the background to figure out if the video ended unexpectedly ahead of time. He's just looking at that. But please go on. Apologies for the interruption.
Matrix form structure. Actually, BDEFH, that means top, bottom, left, right, and central parameters of the node. And
okay, it looks like Jim found the remainder of the video, so let's go ahead and cut back into the recording.
Alrighty, thanks, Craig. Apologies for that, Yilmaz. Let's continue.
Okay. And we also have which number of the nodes is this. So east, west, north, and south nodes have numbers here. And this is the successive over relaxation method, how we calculate all nodes here. This is single core model. And if you want to do this multi-thread, first you should define class of the calculation threads. And this is our class. We have public worker number, workers, work start and work end parameters. Which line of the matrix you will start to calculate here, and which line of the matrix you will end to stop. You will stop the calculation. And those are the threads that we used here. Here is the application that we generate. There are a lot of unknown nodes, as you see. Those are shown in vector form. And we have a block which is shown in yellow color in the middle of the flow. So we want to see what happens in front of the flow, in front of this block and behind the block. So we want to simulate this. As a result, after calculations, we obtained different views of those fluids' behavior in different time periods. At the end, you can see vortexes and vector changes on the form, and we also obtain graphical results in color modes for the U, R, and P parameters. And now let's see how this theory and method is working with C++ Builder. This is built with VCL form, and actually in 1999 that was the first build, and it wasn't accepted, but I spent a lot of time, so I want to show this old version here. In this old version, it's also built with C++ Builder, and you can see each nodes here. For example, those are pressure nodes here, and each node has value at the start. This is fluid flow, and also we have vectorial form here. So you can see each vectors on the fluid form, and when you calculate, you can see uniform fluid flow here, and you can also add some blocks here like this to see what happens when there's a block inside the fluid flow. As you see, it is working very fast, but there are no vortexes behind this block here. But it is very nice to show how fast C++ Builder is calculating, because there are a lot of unknowns and there are very big matrices to solve, and it's solving each nodes very fast with many iterations. You can also see iterations, how many iterations done to achieve the enough approach. So it is very nice to see what happens when there's a block here. Now let's see our current version. This is a little bit simplified, and it has only one block. You cannot draw a new one, but it is much more robust version. And as you see, it is calculating a little bit slower, but grid size is much more bigger than the previous one. And you can see how it calculates and how it iterates the parameters here. This is our matrix form here, and Our grid size is 120 and 64 nodes, and okay, this is the timer that calculates U values, V values, and pressure parameters. As you see, we calculate the U direction vectors, X direction, and pressure parameters. This is how it works. As a result, I want to introduce some books here if you want to calculate CFD in numerical methods. First one is Computational Fluid Dynamics, and other one is the Numerical Heat Transfer and Fluid Flow. And if you want to add some heat transfer also, you can use Computational Fluid Mechanics and Heat Transfer here. And also, if you want to use finite volume method, you can use an introduction to Computational Fluid Dynamics. Also, if you want to be professional about numerical analysis, then numerical receipts in C++, and second edition or third edition would be nice to have in your library. This is my thesis about this study, investigation of flow field in a rectangular duct. It's in Turkish, but I can send you if you want. Just email me. And a numerical study of vortex shading from rectangles is a good study to compare those studies. That's all, and thank you very much. If you have any questions, please ask me by using email. Thank you very much.